Hi, it's Mr. Anderson, and today I'm going to be talking about changes. These changes are physical and chemical changes. And students sometimes struggle telling the difference between chemical and physical changes, and teachers love to kind of ask you hard questions like, let's see, if water is boiling, is that a physical or a chemical change? Or if a mothball vaporizes over years, is that a physical or a chemical change? Or if you mix vinegar and baking soda, is that a physical or a chemical change? So hopefully by the end, I'll give you a few clues that will allow you to answer that. This picture, I decided to start with this picture right here. I live in Montana, and so in Montana, the burgers that we have are pretty good. The steak that we have is really good in Montana, but we don't have In-N-Out burger. And whenever I go to California, I love to get a nice In-N-Out burger because the fries are perfect, get a shake. Oh my goodness, I'm already getting hungry. But when I eat that burger is going to go through two changes. The first changes it's going to go through are physical. In other words, I'm going to start chewing up that burger and making it into smaller little bits. And then it's going to go through my digestive system, and I'm going to start to chemically break down that burger. Now, the cool thing about a burger is that burger will eventually become you. In other words, the amino acids that are in a burger are going to be broken down, and then they're going to use them up inside our body to actually build up the proteins inside our body. And so it's important that you understand chemical and physical changes and the difference between them, because you need to understand how you are made from a burger. Okay, so let's get started. Let's start with physical changes. My definition for physical changes occur when the appearance changes, but the substance does not. And so if we were to look at this pen, for example, is it undergoing change? We'd say, no, it's not changing at all. But let's say that this pen were to change its appearance, but it were still to be the parts of a pen. That would be a physical change. And so how could that happen? Well, if we were to heat this pen up, and so it were to melt slightly, it still would be a pen. If we were to break it in half or bend it, it would still be a pen. In other words, as long as it doesn't combine with another chemical, as long as that substance stays the same, it's a physical change. In other words, if you start with something like water, and we go from water that is a solid, like in this down here, and then we end up with water that it is let's say a liquid. In other words, it starts to melt. Or even if it's H2O that forms a gas, a lot of this H2O inside this ice is actually going to sublimate, so it's going to vaporize and turn into a gas. Well, it's still H2O, and so it's going to be a physical change at each of those points. And so here are some things on the side that I said you could check off if it's a physical change, if it's just melting, if it's boiling, and so I think I have a picture of that. So for boiling water, this always blew me away as a teacher. A lot of people don't know why water boils. In other words, they say, okay, you heat it up and it's going to boil, but they don't know what's inside the bubbles inside boiling water. And so what is inside the bubbles inside boiling water? Well, it's not hydrogen and oxygen gas. That'd be bad, because if it was hydrogen and oxygen gas, once they come out, would quickly combust. Hydrogen is going to combust and explode, and we know that doesn't happen. And so what's actually in the bubbles in boiling water? It's simply water vapor. In other words, it's water that is in the state of a gas. And so we would say not a chemical change, that's a physical change. Or if we were to, for example, break these bricks in half, or keep breaking these bricks in half and half and half and half and half, and they're still bricks, then we call that physical. Or let's say we were to cut things in half. So if we were to use this torch and to cut this metal in half, the metal here and the metal here would still be the same, and so we call that a physical change to this pipe. Now, right along the point at which you're cutting, if we combine that with oxygen right along that edge, then it's going to be oxidized, and so we call that a chemical change. And then another tricky one that science teachers like to trick you up with is dissolving. So in other words, if I were to take a little bit of sugar and add it to this tea, as that sugar dissolves, in other words, as it goes from this solid to a more surrounded by water kind of a state, we wouldn't call that a chemical change. We call that a physical change. And so It's not a chemical change. And if it's physical change, then we don't have any kind of a chemical reaction taking place. And we don't have a formula. We simply have a change in its state or change in its appearance. And so there's a lot of stuff that's not really a chemical change. So let's get to what a chemical change actually is. Chemical change is when you have a substance that changes. And so, for example, if we go back to water again, if I were to break down water into its gases, H2 and O2, then you'd know that I don't have a water anymore. I have a hydrogen gas and I have oxygen gas, and so we'd know that a chemical change has occurred. In other words, the substance on one side yields, that's what this sign means, yields two new substances on the right, and these would be the products over here. And so we'd say a chemical change has occurred. Now, what are some clues that tell us a chemical change has occurred? Maybe it produces bubbles. And so this right here is mixing acetic acid with sodium bicarbonate, otherwise known as mixing baking soda with vinegar. And what we're getting is bubbles forming, and those bubbles are going to be a new gas. Now, you might be confused thinking, yeah, but you just talked about boiling water and how once that turns into bubbles, then it's a physical change. Well, think about it. Did we have bubbles inside the vinegar? Did we have bubbles inside the sodium bicarbonate? No. And so we've created something new. We've created a gas, and that's what's actually forming the bubbles. And that's what makes the volcano explode when you did this in elementary. Let's say we mix two chemicals together. So we've got chemical A and chemical B, and we mix one chemical, and the other one, which normally was cleared, starts to get kind of cloudy. So we'd say a chemical change is probably occurring. If we ever have clouds showing up, either cloudy liquid or clouds in the air, that usually just means a new particle is being formed, and so a new chemical is being formed. Okay, let's say we get a temperature change. A temperature change is going to indicate that a chemical reaction is taking place. And so the simplest one would be like in methane. Methane is natural gas. It's in a Bunsen burner. And so when we combine that with oxygen, O2 gas, we get some carbon dioxide, we get some H2O, and we get a lot of energy. And so we're creating energy or giving off energy that was stored in the chemical bonds of the methane, and so we would call that a chemical change. In other words, we've increased the temperature. So this right here is pretty cool. We've got two different salts that are probably burning in alcohol, and they're giving off colors depending on what kind of atoms they are. And we would call that a temperature change. The salts by themselves are white, and then as we add enough energy, you get combustion with the oxygen. And so this is how fireworks are formed. We have salts that are mixed up, and then we give them combustion or enough of an oxidizer, and we can get all these different colors. So a color change would indicate that we've got a chemical change going on. And then the last one that would indicate that we've got a change is if we've got, here's a cool one. This is bioluminescence, and so this is adding a couple of chemicals that actually glow. And so we see this in life a lot. For example, we have jellyfish that can produce this glowing protein. So that's chemical reaction. We're mixing chemicals and giving off light. And the last one that I was trying to get to is bread. If you've ever smelled baking bread, there is a chemical change that's going on inside the bread. So all the products by themselves didn't smell that way, but we mix them together, we get chemical reactions going on, and so we've got a smell or a change in state. Now, tasting bread is totally safe, but tasting chemicals in the lab is not so safe, and so I would steer clear of that. This would be a sparkler, and so what do you think? Chemical change? Physical change? Yeah, that'd be chemical. Or going back to a couple of those answers at the beginning that I posed, what about boiling water, chemical or physical? Right answer would be physical. Or what about taking mothballs that you put in your drawer to keep your sweaters, the moths off from eating your sweaters? If that vaporizes over time, what that's going to be, it's going to be a physical change. Okay, and so the last thing I want to leave you with is if we ever have a chemical change, then we have a chemical reaction. And so in a chemical reaction, you're taking these things, which are the reactants. This would be the first reactant, the second reactant, and then we're making products from that. So if we mix hydrogen gas with oxygen gas and create water, then we've had a chemical change. And we usually have to add a little bit of energy to that. Now you should know this. The reactants are on the left side, the products are on the right side, and this arrow stands for the word yields. And so if I were to sketch this out for a second, let's do the hydrogen. Hydrogen is going to look like this. Hydrogen is two hydrogen molecules attached together. And so this 2 right here, this is called the subscript. That tells me that there are 2 atoms of hydrogen in a molecule of hydrogen. This 2 in the front means that we have 2 molecules of that. And so on the left side, we've got 2 molecules of hydrogen gas on the side, but each of those molecules are made up of 2 atoms of hydrogen. If we look over here at the oxygen, I'll draw that a little bit bigger. Oxygen attached to itself, there's 2 oxygen atoms, but there's only 1 molecule of that. And so now let's look at the product. Well, if we look at the product over here on the right side, we're going to have 1 water. So water looks like this. It's got a hydrogen and a hydrogen. It's got another water here. Hydrogen, hydrogen. And so if we count them up, we should have the same if it's a balanced equation. So how many hydrogens do I have on the left side? 1, 2, 3, 4. How many hydrogens do I have on the right side? 1, 2, 3, 4. So that's balanced. If we look at the oxygens on the left side, we've got 1, 2. On the oxygens on the right side, we've got 1, 2. And so that's a balanced equation. And so I've got a podcast on balancing equations that you can take a look at if you don't know how to do that. The key thing is that you can always change the coefficients. This would be a 1 right here. You can always change what comes before the formula, but you can never change the subscripts. Because if you're changing the subscripts, it'd be like breaking that oxygen in half, and we know that that doesn't occur. So I hope that's helpful. Those are chemical and physical changes.